Okay, so let's move into a new topic. Properties of definite integrals. Now, in this particular lecture video, this theorem is going to help us find the antiderivative of piecewise functions. We've dealt with piecewise functions before. It's one function broken up into 2 or 3 pieces or even more pieces. This section is going to show us how to take the integral to anti-differentiate piecewise functions. So Theorem 5 is a very important theorem, so let's look at it. For A, I'm just going to rephrase this. For C, some number C between A and B. Okay? Notice it's not equal to. If it's equal to, it's not really somewhere in between, is it? The antiderivative, or the integral from a to b of the function f of x with respect to x, can be rewritten as the integral from a to c. Remember, c is somewhere in between a and b, right? The integral from a to c of f of x dx, and then the integral from c to b of f of x dx, and then I add those two together. So I can split up the original integral if I need to. I can split up the original integral from a to b, in this case 2 pieces, from a to c and c to b, since c is in between them. So notice what I've written. For any number c between a and b, the integral from a to b is the integral from a to c plus the integral from c to b. Now, let me show you visually what I'm talking about. I drew a function and I just used first quadrant. And on the x-axis I have a to b, and I drew the function, whatever it is. Here's what this particular theorem is actually talking about. If I have some number c, and I'm going to put c right here, between a and b. It doesn't matter where it's located, all I know is it's between a and b. And this antiderivative is telling me that I could take the integral from a to c. Remember, the integral is the area under the curve, right? So from the function to the x-axis, from a to b, if I figure out the integral from a to c, so I've got the area under the curve, between the curve and the x-axis from a to c, and then I take the integral from c to b. Remember, this is still the area under the curve from the curve to the x-axis, and if I take that integral and add them together, I'll get the entire area under the curve to the x-axis from a to b. Good? Okay, let's put this into practice with an example. So let's look at this first problem. The directions say to find the area under the graph of the function. So they've given me a function, and notice it's in pieces. Surprise, surprise. The first piece says that it is, or the function for the first piece is 2x plus 1, as long as x is less than or equal to 3. The second piece says we're going to use the function 10 minus x for x greater than 3. And they'd like us to find the area under the curve, the area under the graph of the function, in this case over the interval 1 to 5. So here's what I'm hearing them say, that they would like us to find the area, so I'm going to put a of x, of the function, and I'm just going to write f of x with dx with respect to x. The interval is from 1 to 5. Agreed? Now, if I take a look from 1 to 5, I'm noticing that neither one of these pieces deals with the entire interval from 1 to 5. I'm noticing that the first piece, 2x plus 1, is only allowed to be used for numbers less than 3 or equal to 3. The other piece is allowed to be used for x's that are greater than 3. So here's what I'm seeing. I'm seeing the fact that I am going to have to anti-differentiate in this case 2 pieces. The first piece is going to go from 1 to, what do you think? 3, because 3 is in between 5 and in between 1 and 5, and since the piecewise function has used the number 3 as the breaking point, so to speak, as the stopping point of one function and the start of another function, we are going to go from 1 to 3 on the first integral. And the function that allows me to use the numbers from 1 to 3 is which function? The 2x plus 1 or the 10 minus x? Good, the 2x plus 1, because 2x plus 1 is allowed to be used for x's that are less than or equal to 3. Good? Okay, and then I'm going to add to it the other piece of the puzzle. Now the other piece of the puzzle is going to start at 3, and it's going to end at 5. Now, which piece of the puzzle, so to speak, which piece of this function allows me to use x's that are from 3 to 5? The 2x plus 1 or the 10 minus x? Yeah, the 10 minus x, because the 10 minus x is used for numbers that are greater than 3. And some of you are like, but wait. That one doesn't say x is equal to 3, so yes, I understand that. But remember, this is going to work itself out because this part's going to get subtracted off, right? So I don't have a duplicate going on. And the function I'm using for the integral from 3 to 5 is 10 minus x dx. Good? Okay. Now, you know as well as I do how to take the antiderivative of each one of these. So let's look at the first one. So I am going to take the antiderivative of 2x plus 1. What do you guys get? Yeah, you just get x squared, right? And the antiderivative of 1 is x. And you're going to evaluate this from 1 to 3. Good? All right. And then you're going to add to it the antiderivative of 10 minus x. So what's the antiderivative of 10? Good, 10x. What's the antiderivative of x? Good, 1/2 x squared. And then you're going to evaluate it from 3 to 5. Agreed? Wonderful. Okay. So at this point, it's just a lot of plugging and chugging, so to speak, right? All right, so let's work this out together. So I'm going to plug the 3 in first. So 3 squared, that's 9, plus 3. And then I get to subtract off. So I'm going to put a parenthesis around the 9 plus 3. And then I have to plug in the 1 and subtract it off, right? So we have 1 squared, which is just 1. And then plus 1, right? And then close that off. That's my first part, correct? Okay, so now let's look at the second piece. The second piece, for the 10x minus 1/2 x squared, we plug in the 5 first. So what's 10 times 5? Good, 50, minus 5 squared? Yeah, that's 25 times 1/2, which is just 25 over 2. Yes? And then we're going to subtract off from it. Plug in the 3. Good, that's going to be 30 minus the 9 over 2. Excellent. How are we doing? So at this point, let's work on our algebra, right? So on the first part, we have 12 minus 2. Easy peasy. The second part. Now this one has fractions, and so you're going, oh my gosh, common denominator. I get it. But do you notice the two fractions actually have a common denominator? So check this out. I'm going to work smart, not hard. So I have 50 minus 25 over 2. Now distribute the minus sign. Minus 30, and that becomes plus 9 over 2, does it not? Okay. So the first parenthesis just turns out to be 10. I guess I don't need the parentheses anymore. So let me erase that parenthesis that I put before the 10. Okay, now in the second parenthesis, we can combine the 50 minus 30, which is just 20. Now help me out here. What's a negative 25 plus 9? Yeah, that's a negative 16. So that's negative 16 over 2. Well, what's a negative 16 over 2? Yeah, minus 8, isn't it? So check it out. So we're going to have, I keep wanting to put that parenthesis in. Let me get rid of it. We don't need it anymore. We have 10 plus 20 minus 8. Agreed? Good. So what's 30 minus 8? 22. Cool? Okay, so 22 is the area under the graph from this piecewise function to the x-axis. Got it? Awesome. Got another one. So let's look at this next example. They're still asking us to find the area under the curve for this particular function, in this case over the interval from negative 2 to 3. So notice it's in pieces, right? So what's going to be that number in between the negative 2 and 3? Yeah, it's going to be the 0 because that's where the function splits apart, is at the 0. Correct? All right. So we know that it's going to be from negative 2 less than 0, less than 3. So the area under this curve is going to be the integral from negative 2 to 3 of the function g of x dx. Now the question is, does one of these pieces cover the entire interval from negative 2 to 3? No, it does not. So we've got the same situation as we had in the last example. We're going to start at negative 2 and we're going to go to 0 for the integral. Now, the question is, which piece of this piecewise function, which of these pieces uses the numbers from negative 2 to 0? Is it the first piece, x squared plus 4, or is it the second piece, 4 minus x? Good, it's the first piece, x squared plus 4, because it says to use that piece for x less than or equal to 0, correct? Okay, so my first integral from negative 2 to 0, we are going to anti-differentiate the x squared plus 4 with respect to x. And now we have to go from 0 to the 3. Now, which piece of this function uses the numbers from 0 to 3? Yes, the second piece, the 4 minus x, because it says use that piece for x greater than 0, right? Okay, so 4 minus x dx. Are we in agreement so far? Loving it. Okay, so here we go. We're going to anti-differentiate the x squared plus 4. So when we do that, what's the antiderivative of x squared? Good. 1/3 x cubed. What's the antiderivative of 4? 4x. And we are going to evaluate this from negative 2 to 0. And then the second piece, the second integral, what's the antiderivative of 4? Good, 4x. What's the antiderivative of x? Good, so minus 1/2 x squared. And we're going to evaluate this from 0 to 3. Okay, we're doing good so far. So let's look at the first one, 1/3 x cubed plus 4x. So we plug in the 0 first. What do we get? Yeah, that's just going to be 0 all the way around. And now we're going to minus. So we plug in the negative 2. So negative 2 to the power of 3. Negative 8 times 1/3, negative 8/3. And now we plug in the negative 2 to the 4x. What do we get? Negative 8. Awesome. So there's the first piece. Agreed? All right. Second piece. We plug in the 3 to the 4x. What do we get? Good. We get 12. And then we have to plug in the 3 to the 1/2 x squared. What do we get? Yes, 9/2 minus, and now we plug in the 0, which is just going to give me 0. So it's nice to have that 0 there to plug in. It creates less work, doesn't it? Okay, so back to the first piece. So 0 minus. So I am just going to start distributing that minus sign. So that's a positive 8/3, and that's a positive 8. Correct? On the second piece, we have plus 12 minus 9/2. Yes? Okay. And now I'm just going to add my like terms that I can do very quickly. I have 20 plus 8/3 minus 9/2. Unfortunately, the 8/3 and the 9/2 don't have the same denominator. We have to get a common denominator. So I'm assuming you remember how to get a common denominator. Do you? Good. What's a common denominator? 6. Yay! All right, so here we go. 20 plus 8/3. You're changing to denominator of 6. Yeah, top and bottom get multiplied by 2. So we got 16/6 minus 9/2. Need a denominator of 6. Top and bottom by 3. So 27/6. So what's 16 minus 27? Good. 20 minus 11/6, right? Okay. Now, if they want me to write it as a mixed number, I'm well on my way to be able to do this. This would be 20 minus, what is that? 1 5/6. So, when you subtract this, yeah, this would be 18 and 1/6, wouldn't it? And some of you are like, wait, how'd you get that? Okay, so if this part has messed you up, going from 20 minus 1 5/6 to the 18 and 1/6, then here's my recommendation. My recommendation is take the 20 minus 11/6, get the common denominator. So I'm going to change the 20 into 120/6 minus the 11/6. Subtract, what do you get? Good, 109/6. And when you convert that to a mixed number, you will get the 18 and 1/6. So if they want the answer as a fraction, 109/6. If they want the answer as a mixed number, 18 and 1/6. So either way you figure this out, you get the same answer. Good? Awesome. Got another one, and this one is actually dealing with absolute value, which makes life interesting. All right, this third one actually is asking me to take the antiderivative from 0 to 4 of the absolute value of x minus 3 dx. Now, we have not had any anti-differentiation rules that have allowed me to anti-differentiate an absolute value. So, we have to figure a way on how to approach this. Because if you remember, when you solve absolute value inequalities or even equations, it's not one equation or one inequality that you are solving. You end up splitting the absolute value up into two different equations or inequalities, don't you? Okay. So I know you're going, well, okay, why am I solving in this case? Why is she asking me to remember how to solve an absolute value inequality versus an equation? Well, an equation means that this would just be equal to a single number, wouldn't it? If I change that to the absolute value of 2x plus 1 equals 7, that is asking me to equal it to just one number. The integral is from 0 to 4, that's an interval. So considering they're asking me to take the antiderivative of an interval, that means I don't have an equation, I have an inequality, because the inequality works with an interval, not just one number. Good? So I am asking us to remember how to solve an absolute value inequality, because this will give me an interval to work with, just like the original problem is an interval. Now, we'll get to this integral in just a minute, so just leave it off to the side. I'll be back to it. I just want to make certain that you remember how to solve an absolute value inequality, because I'm going to need to remember how to solve that in order to handle that integral, believe it or not. So here we go. Remember how to do it? Need a refresher. Got it. So one of your inequalities will be the 2x plus 1 less than 7. Remember, absolute value means it doesn't matter what you plug into the function inside. When you take the absolute value of it, it will always be positive. So the other inequality is 2x plus 1 is greater than negative 7. Remember? Okay, you're like, okay, ringing a bell. So when I solve the 2x plus 1 less than 7, I am going to get that x is less than 3, right? When I solve the other one, I am going to get that x is greater than, whoops, looks like negative 4. So it gives me an interval to work off of. X is greater than negative 4, x is less than 3. It gives me an interval to work with. Good? Okay, so now that you've remembered how to solve an absolute value, for us to be able to work with the integral of an absolute value, I literally need to split the absolute value apart so I can put it into a piecewise function and handle it. Just like we did over here, it's like, oh, this piece I work with for x less than 3. This piece I'm going to work with for x greater than negative 4. Okay, got it. Absolute value of x minus 3. You're like, what are you going to set? I'm going to use that bottom number of 0. Okay? I want to have this be greater than 0 because we have from 0 to 4. But when I get the other inequality, we're going to have x minus 3 is less than or equal to a negative 0, just like we had over here. Well, we'll be back to that one. That one kind of doesn't make sense, but hang in there. So here we get x is greater than or equal to 3, don't we? Over here, we get that x is less than or equal to, let's try that again. This negative 0 doesn't make sense, does it? Okay, so I'm going to bring this negative sign back over so it makes more sense. So I'm going to multiply both sides by a negative. So I end up with negative x plus 3 is greater than or equal to 0, don't I? Which, when I solve, will give me x is less than or equal to 3. This inequality makes sense because I can't have a negative 0. That doesn't make sense. Negative x plus 3 is greater than or equal to 0. That makes sense in terms of how to write it. X minus 3 is greater than or equal to 0. They both match up. They're both greater than or equal to 0. But when I solve, I end up with two different intervals, don't I? So here's the deal. The function is going to be split. So I'm just going to call the function f of x. The function f of x is going to be split into x minus 3. And I can use the x minus 3 for x greater than or equal to 3. And the other one is going to be negative x plus 3. And I can use that for x less than or equal to 3. Cool? Okay, so we can't have both of these with the equal to sign. And you're like, well, which one is not going to have the equal to sign? It's going to be this second one where we said x minus 3 was less than or equal to a negative 0. We're going to make it the second one. We usually make it the second one. You're like, why is that? X minus 3 greater than or equal to 0, that's the original. The original was greater than or equal to 0. It went from 0 to 4. So on the second one, I am not going to let the equal to sign be there because it wasn't, the original interval wasn't less than. Okay? So that means your negative x plus 3, this is the one that will not have the equal to part. Cool? Okay. Now I've got my function. Now I'm ready to split it apart. So, let's take care of this. The interval is from 0 to 4, isn't it? 0 to 4. But it's breaking at 3. So we are going to go from 0, less than 3, less than 4. That's how we're going to set it up. So we have got the interval from 0 to 3 of the negative x plus 3 dx, plus the integral from 3 to 4 of the x minus 3 dx, because that's how we wrote it up. Cool? All right. So, doing your work, antiderivative of negative x. Good. Negative 1/2 x squared. Antiderivative of 3, 3x. And we'll evaluate it at 0 to 3. Plus the second half, okay, what do we get? Follow along. Yeah, 1/2 x squared minus 3x. And it would be evaluated at 3 to 4. Good? Okay, so let's see. What do you guys end up with? Plug in the 3. Yeah, we'll have negative 9 over 2 plus 9 minus 0, so I don't have to worry about that. On the next one, you're plugging in a 4. So what is that, 4 squared? So we have 16 over 2 minus 12. And then we got a minus whatever we get when we plug in the 3. Yeah, that looks like 9 over 2 minus 9. Okay, ready? Here we go with some more of our algebra. I'm just going to start doing some distribution here. So that's a negative 9 over 2 plus 9 from the first part, plus 16 over 2 minus 12. Distribute the minus sign here. That'll give you a negative 9 over 2 plus 9. Agreed? Okay. I'm going to start collecting some like terms. The 9, the negative 12, and the 9. So is that 18 minus 12? Good. 6. And then I'm going to collect some other like terms. We have negative 9 over 2, another negative 9 over 2, which is negative 18 over 2 plus 16 over 2. Sounds like a negative 2 over 2, which is what? 6 minus 1, which gives me 5. Cool? Okay. I know this part is easy for you. It's getting to this function f of x where the absolute value was split into two pieces. You need to remember how to solve an inequality. Here, on the original one, we have the absolute value of x minus 3. The bottom of it was at 0. So I was going to set the original function greater than or equal to 0 because the interval was greater than or equal to 0. And the second inequality was actually a negative x plus 3 greater than 0. And that ended up with this function, this piecewise function right here. Cool? Okay. If you need to rewind this particular problem so you can listen to it again. All right. I'm going to be working with another theorem. And this theorem is going to be talking about finding the area under a graph. You know, like, isn't that what we've been doing? Yes. But what we've been doing is finding the area under a graph to the x-axis. The next theorem is finding the area between two graphs.